In the previous class, we looked at the propagation of waves, or rather how the waves are inside a medium that has some conductivity. We started the discussion and we said that while a perfectly good dielectric or a perfect insulator is very similar to a lossless transmission line, conductive medium introduces the concept of loss, or what we call as the attenuation in a transmission line or a lossy transmission line. So we saw that for a conductive medium, the epsilon essentially is a complex quantity, and with that we also saw that how at different frequencies the medium may have more conductive properties, and at some frequencies the medium may have more of dielectric properties. So the concept of frequency dependent behavior essentially comes in. So let us continue the discussion. So we ended the last class rather abruptly with an expression. So we had said that for a good conducting medium, so the conductivity sigma is much more than the omega epsilon 0, this quantity. So essentially this is beyond or much above the transition frequency which we had defined in the previous class. We had also defined something called as loss tangent. So in a nutshell, long story short, this essentially indicates that the conductivity is very high. So what we had discussed was the propagation constant gamma, or gamma square. What we had written is nothing but minus omega square mu times epsilon, where epsilon will now be the effective complex epsilon for the whole medium. So that is epsilon r minus j sigma by omega epsilon 0. So just opening the bracket and regrouping the terms, we had actually derived that the gamma square reduces to j omega mu times sigma plus j omega epsilon 0 epsilon r. So essentially it is this condition is not just for omega epsilon 0 but the epsilon for the whole medium. So what this indicates is that the conductive nature is much stronger than the dielectric nature. So what essentially we are seeing is that if this is the case, the real part will dominate over the imaginary part. So therefore this would look something of this kind. So this is what is gamma square. So this we can write it as omega mu sigma. These three are all real values, and j means the phase is pi by 2. So using Euler's entity, we can write e raised to j pi by 2. So now gamma square is this. So therefore gamma will be the root of this. So it is nothing but the root of the omega mu sigma as a quantity, that is the magnitude, and the half of this angle. So essentially gamma will look like this. So if you expand this, what you will if you expand this in the Cartesian form, what you will see is the cos of pi by 4, that is 1 by root 2, plus sine of pi by 4, which is also 1 by root 2 but with a j. So this is what we get. So now what we are seeing is, for a very good conducting medium, essentially the gamma reduces to this. So if we are opening it, if you are opening the bracket, what we will see is so what we can say, since this is gamma, the real quantity is the alpha and this imaginary quantity is the j beta. So the magnitudes of alpha and beta are pretty much the same. So now let us understand that what is the physical implication of this. Let us move one step ahead of the math that we have derived and try to see what is going on. Now let us say we have a conductive medium. Let us say that the conducting medium starts from here. So let us say that the wave starts propagating inside the conductor in this direction. The wave is essentially propagating starting from the boundary directly into the conductor, and the direction is normal to the conductor boundary. Let us not worry about how the wave got there, but let us say that this is what it is. So now something tells me that since the alpha is non-zero, in fact it is a significant quantity, the magnitude of the wave will die down as it keeps propagating inside. So somewhere, very similar to what we had defined for transmission line, the magnitude will reduce as we move inside the medium more and more. So now, what is the way in which the magnitude reduces? So the magnitude reduces proportional to e raised to minus alpha z. Now let us assume that this is the z direction. So suppose if the initial magnitude, initial means just at the starting, if the initial voltage, or rather the initial field, is given as something of this kind, E0 plus e raised to minus alpha z, or when z is equal to 0, the magnitude will be E0 plus. So now we are interested in that distance or that value of z after which the magnitude of the field essentially becomes 1 by e times the initial field. So to have it 1 by 3, the power of e must be equal to minus 1. So the distance over which that happens will be nothing but 1 by alpha. So what we can say? We can say that since the field or wave magnitude changes as a function of e raised to minus alpha z, the value of z for which the magnitude becomes 1 by e times the initial magnitude, and that value of z is nothing but 1 by alpha, because if z equals 1 by alpha, it is called, or rather the power of e will become minus 1, hence we get 1 by e. Now this distance, that is like saying I have this conductor boundary, let us say a distance equal to 1 by alpha, where the magnitude essentially becomes 1 by E times the initial one. Let us say this is 1, this is 1 by E. This distance is like, has a very special name. It's like giving an indication that, okay, if somehow a wave starts propagating inside the conducting body, this is the conductor boundary, inside the conductor boundary, the wave starts dropping in magnitude. And in some sense, this is an indicating that by the time the z becomes 1 by alpha, the magnitude has reduced quite a bit. So it's like saying effectively, the wave is able to penetrate only this distance for all practical purposes into the medium. So it is like saying, if a wave is vertically traveling into the medium, the depth at which it is able to penetrate is given as this quantity 1 by alpha. So this quantity is called as skin depth. Why skin? Because if you assume that the medium is infinite on this side, that is z can tend to infinity, most of the field or the wave gets limited to very near the boundary of the medium. So it's like saying the wave energy essentially dissipates near the skin or the boundary of the medium. So therefore this depth is called as skin depth. It is essentially giving an idea of how much the wave is able to penetrate into the medium. So this skin depth, or the depth which is at which the wave is able to penetrate into the conducting media for all practical purposes, is nothing but 1 by alpha. So alpha we already had derived what it is. So this is nothing but 2 by omega mu sigma. So this is what it is. Now this skin depth has a very practical application, and many a time we have used that application, but perhaps without realizing that this is what is happening. Now you will realize that there are many kitchens which have a microwave oven. So if you have a microwave oven at home, you may know this. If you don't have, don't worry. Just go to the microwave oven. If you don't have one, just go online and look at its user manual. Most of the microwave ovens will say that do not use a metallic vessel to heat up or cook your food inside the oven. Now that has multiple reasons why. One of the reasons is this. Now let us take an example and see how. The microwave oven works at a frequency. Microwave means it is also an electromagnetic wave which is used to heat up your food. So if you don't know, then the frequency at which your microwave oven works to heat up your food is about 2.45 gigahertz. So now let us say I take a thick metallic vessel and I put it inside the microwave oven with some food inside it to cook. And let us say the microwave source is hitting that metallic vessel body. The question is, how deep can the wave propagate inside the metallic body? So that is given by the skin depth. So now depending on what the material is, the skin depth will be this, which is 2 divided by omega, that is 2 pi into 2.45 into 10 raised to 9 into mu into sigma. Now mu is a small value, sigma may be a large value because of the metal, but these two will kind of cancel out the effects of each other. Effectively the skin depth as you can see, because of the very large numerator, because of the very large denominator, the skin depth will be very low for metals. So therefore, if you are using a very thick metallic vessel to cook the food, chances are that the wave will not propagate into the metal and therefore it will not even reach the food. The exception is obviously when the microwave source is sitting right above and it will hit the food even without the vessel, but I am just talking of a simpler example or a special case. So therefore this is something you should know. So the skin depth inside metals is rather poor because most of the wave essentially gets dissipated near the boundary of the metal. So what you will see essentially is that if such a thing happens, your metallic body will get heated up, but not the food inside it. So the exception is of course if the metal thickness is very small, it is even smaller than the skin depth, then certainly the wave can penetrate through and it might cook your food. So, but if that is not the case, then we cannot say anything. So therefore that is one of the reasons why the user manual mentions that do not use metallic objects inside. So now what we saw is for a good conductor or a good conducting medium, we saw that alpha is equal to beta, which is nothing but omega mu sigma divided by 2. So now if I ask you, suppose the wave is traveling inside this conductive medium, let us say near the boundary if it so has to be, what is the velocity of the wave? So the velocity of the wave as you very well know by now, the wave velocity or v is nothing but omega by beta. So this is equal to, you know what is beta. So if you just divide omega by this quantity, you will get the 2 will go up, so you will get 2 omega divided by mu sigma. This is the wave velocity. So immediately what can we see? We can see that the wave velocity is a function of the permeability and the conductivity. Since conductivity is much more than the epsilon of the medium, so that does not really come into picture over here. The other thing that we can see is that the wave velocity is a function of omega, or in terms of frequency I can write 4 pi f divided by mu sigma. So here the wave velocity is a function of the frequency. So any medium where the wave velocity is a function of frequency is called as a dispersive medium. Recall what was the velocity for the wave in the dielectric medium. That was 1 by under root mu epsilon. That had no component of the frequency, or it was not at all dependent on the frequency of the wave that is traveling. So therefore a perfect dielectric is non-dispersive. Now dispersive means what? If a signal has multiple frequency components and the medium is dispersive, then dispersion will happen. Now what is dispersion? You may recall dispersion from your school physics, that is when a ray of light passes through one medium to another, let us say through a glass prism or something of that kind. The white light essentially gets split up into its different constituent colors. Why? Because the colors from violet to red, they all have different frequencies. And the glass is essentially a dispersive medium. So because of its properties, so what happens is that the different frequency components in that ray of light, they travel at different speeds, and therefore you are able to sometimes see how the different colors are looking. So this is no different. Here also dispersion means the same thing. So the phenomena is dispersion. So that means different frequency components in a signal travel with different speeds. Now this is particularly dangerous when the wave that you are sending from one end to another end is a non-sinusoidal wave. For example, if you have a square wave or a triangular wave, that is waves which have more than one frequency component as per Fourier's theorem. So therefore what you will see is that if a square wave is traveling through this kind of a medium, it will not remain a square wave anymore, because the different frequencies will travel with different velocities, and what you will get at the end is a totally distorted signal. So that is how it works. So now let us write down what we have understood so far in terms of the velocities. So the wave velocity, let's take case 1 in free space. So that velocity is nothing but 1 by mu 0 epsilon 0. So in any homogeneous good dielectric, good dielectric means the conductivity is 0. So therefore the velocity is nothing but 1 by mu 0 epsilon r times epsilon 0, where epsilon r is the permittivity of the dielectric, relative permittivity. Now third is in a good conductive medium, so where sigma is much more than omega epsilon. We just proved that it is nothing but 2 omega divided by mu sigma. Now this is a dispersive. Fourth, in a lossy dielectric, that is sigma is not equal to 0, but it is not very large also. So it has both dielectric and lossy properties. So how can we find out the velocity in a lossy dielectric? So we can find out the velocity by writing the propagation constant gamma. So in the previous class we had written this, where the epsilon essentially is, I should say this, and epsilon effective is complex. So because more than the conductivity, it is the epsilon which defines a dielectric. So the gamma, if you remember, was something of this kind. In that case, mu epsilon 0 times the root of the epsilon effective, and that was epsilon r minus j sigma divided by omega epsilon 0. So what you can do now is you can actually take the square root of this complex quantity and then using that you can find out beta. So I leave it to you as an exercise to find out beta and then use suitable power series approximations to find that the velocity is actually, I leave it to you as a proof exercise, that the velocity is nothing but 1 by, it's very similar to this, mu 0 epsilon r epsilon 0 times 1 plus sigma square divided by 8 omega square epsilon 0 square epsilon r square the whole raised to minus 1. This is the wave velocity in a lossy dielectric. You can also see that this is a function of omega, which makes even lossy dielectrics dispersive. So, good conductors or lossy dielectrics, the moment you have this conductivity term, the medium becomes dispersive. But for very good dielectrics, the medium is not dispersive. So, now we can say, based on our knowledge so far and also the knowledge of physics that we have gained in high school, we can define something called as the refractive index of a medium. The refractive index of a medium, in simplest terms, you know, you can define it using Snell's law, but without doing that, we can define it in terms of the wave velocities also. So we call that refractive index as n, so which is nothing but the ratio of velocities in the two medium. So it's velocity of wave in vacuum or free space, whatever, divided by velocity of wave in the medium. So therefore refractive index, as you can see, will be always more than 1, because no wave can travel faster than that in vacuum. So this is how we define. Now, since you know the velocity expressions for different kinds of medium, you can essentially substitute those velocities, and as a function of either frequency or of the properties of that medium, you can find out what is the refractive index. So now let us continue this discussion about good conductors. So again, let us consider this conducting boundary. Where we can say that sigma is much more than omega epsilon. So we can define the positive z axis this way, and let us say that again the wave starts propagating this way. It's just come in and it is starting to propagate. So let us say that the electric field component of this wave is a function of z, as you know, and let us say the magnitude of that electric field, let us not bother with the vector sign right now, we can just say it is some E0, and it changes as a function of z, it reduces, so it is minus gamma z, where we had defined that for very good conductors, gamma is nothing but this is what it is. So now what will happen is, because of this electric field which is entering the medium, there will be some current due to the electric field, because the medium has finite conductivity sigma, and the moment you have some electric field E, there will be some current density which is, let us say, J, because the electric field is moving this way, even the J will be a function of Z, and that is nothing but sigma times E of Z. So that becomes sigma E0 e raised to minus gamma Z. So but as per boundary condition, and also the effect that we saw just a few moments back, that most of the field is limited near the surface of the metal. That effect is also called a skin effect. So since we defined something called a skin depth, we can define the effect as skin effect. So we can actually define that. So this we can define as skin effect. So because of the skin effect, most of the field will be limited over here near the surface. So there will be some current density, but we can actually try to represent that current density as in the form of surface current rather than the actual current in the medium. So we can actually say that this current, the surface current, is nothing but the volume current which essentially exists near the surface but is a function of Z. So if we consider a small incremental distance, so what will essentially happen is that if you are assuming that the wave is entering at this point, most of the field and the surface current will be limited in this area. So essentially what we can say is the surface current density Js, which is also a function of Z, we can define it using integration. We can say we can integrate it over the whole Z axis from 0 to infinity, because Z is starting from 0 and is going forever. That is this J of Z dz. Remember, the unit of J is amperes per meter square and unit of surface current is amperes per meter. So dimensionally this makes sense. So what we can say by substituting this, if you substitute this and apply the limits, what you will get is the exponential will stay the same, but the gamma will come in the denominator. So the expression will essentially turn into sigma by gamma times E0. So now we know that even though the wave is propagating along the Z direction, the electric field vector is a function of Z but has to exist in an axis that is perpendicular to Z. So it can exist along the x-axis, it can exist along the y-axis, that is immaterial. The important thing is the electric field has to exist perpendicular or orthogonal to the z-axis. So now whether the electric field exists this way or it exists this way or this way, it doesn't really matter, because as far as the surface is concerned, the electric field will always be tangential. So if we now look at the surface, we know that this is the surface current density. So the electric field at the surface is when this electric field is calculated at z equal to 0. So the electric field component at the surface is nothing but E0, and that is tangential. So I can say the tangential E field at the surface is nothing but E0. Why? Since Z is equal to 0 at the surface or the boundary. Now what is the unit of E0? Volts per meter or electric field. We just calculated the surface current density Js, that is equal to gamma by sigma times E0, and the unit of surface current density is amperes per meter. So if I now take the ratio of the electric field at the surface with the surface current density, I am going to end up with what we call as the, or rather I am going to end up with a quantity that has the dimensions of impedance, because I am dividing volt with ampere. So now we define this quantity called as surface impedance. Of the conductor. That is nothing but E tangential divided by Js at the surface, which are both. So if you divide, you will get essentially it is oops, I wrote it in the wrong way. This is actually sigma by gamma. So if you divide the two, what you will get is essentially that the E0 terms will cancel out, and you will get gamma by sigma. So now this we can define as the intrinsic impedance of the conductor. Why? Because the fields are limited near the surface. So the surface impedance is limited, or rather the intrinsic impedance is limited to the surface. So which is also defined as the intrinsic impedance Now since the E field, as we saw, that it is existing near the surface or the boundary, the H field which is associated with the wave will also have a very similar nature, and both will decrease drastically as you move into the Z. So therefore, in the region where the fields are more prominent, we are defining surface impedance, and that is nothing but the intrinsic impedance of the conductor, or eta C. So therefore, we can actually define this as since we had defined using the Maxwell's equations in the previous class, in general we can say this is the expression for the intrinsic impedance for any lossy dielectric. But since we are talking of a good conductor, this term will have more priority or more significance, and this will cancel out. So therefore what we get will be j omega mu divided by sigma, and we can also write this as multiplying both numerator and denominator by sigma. I can write j omega mu sigma divided by sigma square, that is j omega mu sigma root divided by sigma, And as we have proved already earlier that the gamma of a very good conductor is given as the root of this. So this further clarifies our assumption of naming the surface impedance itself as the intrinsic impedance. So this is also gamma by sigma. So in general, this is a complex quantity, as is the case for any lossy transmission line also. So now we have discussed the basics of the electromagnetic waves, and we also saw how the waves essentially exist in general in a dielectric. We also saw how it exists, or rather how it changes as the medium changes. Sometimes it travels properly, sometimes it behaves in a dispersive manner. So now we know that the direction of the E field, the direction of the H field, and the direction of the wave propagation are all perpendicular to each other. So let us say the E, the H, and the direction of propagation are orthogonal to each other. This I am talking about only, let us say, in the simplest case, that is the homogeneous dielectric, which is infinite in size. So if you recall, a couple of classes back we had actually defined this way. Let us say this is the x-axis, this is the y-axis, this is the z-axis. So if the electric field vector essentially changes over here and the magnetic field vector changes along the y-axis, then the cross product of E and H will essentially point towards the z-axis. So we had discussed that the E cross H direction is the direction of propagation. So likewise, if you remember, if E and H are both negative, so again then you will have something of this kind, using the right hand thumb rule for cross products. Now let us say that I have a medium which need not be a perfect dielectric nor a perfect conductor, but in general the fields do exist in the medium. Now let us try to see how the fields exist and how the wave is propagating. So again, as you know, the fields are given using the Maxwell's equations. So let us say the medium has some sigma, it has some mu, it has some epsilon. Now these are the quantities which define the properties of the medium. So we can apply the Faraday's law and the Ampere's law and we can write this. So using Faraday's law, I can say that curl of E is nothing but mu times del H by del T, and the Ampere's law is J plus epsilon del E by del T. I am using the differential forms because I am assuming that let the medium be continuous, homogeneous, and infinitely large. So now going back to the statement which I made, that the E cross H is telling me the direction of propagation. But apart from the direction, E cross H also has some magnitude. Now the question is, apart from giving us the direction of the wave propagation, does the quantity or the magnitude of E cross H convey some additional information also? So when E cross H is pointing towards the direction of propagation, so when we say a wave is propagating, what is propagating? There are no charges, for example, even though there may be charges in general, the wave cannot make those charges move. But let us say in a medium, even where there are no charges, the wave still exists. So what is moving? It is essentially the energy that is carried by the wave. So, or what we can call as power also, which is energy per unit time. Now the question is, if we were to have the direction of flow of energy, so we can also write direction of flow of energy or power. So there is no reason to think that the value of E cross H would also give us anything different. So since the E cross H is a vector on this side, I would like to know how much is the outward flow, or since I'm talking about flow of energy or power, I would like to know what is the flow of this vector. So the moment we talk of flow, we talk of the quantity called divergence. So if I say that the net flow of energy or power, so I can take the divergence of the E cross H vector. Now before I do this, what is the unit of E? Unit of E is volts per meter, and unit of H is amperes per meter. So if I multiply volts per meter by ampere per meter, what will I get? I will get volt into ampere divided by meter square, and volt into ampere is nothing but watt. So I can say that the E cross H, the unit will be watt per meter square. So in some sense it is telling me the power per unit area. So this is also called as power density. So now let us use the laws of vector calculus. So the divergence of a cross product is nothing but this. You can actually prove this. It is very straightforward. So now we already know what are these two quantities because of the Maxwell's equations. So what we will get, let me write it on a new page. So this is equal to H minus mu del H by del T, and this is J plus del D, or I'm sorry, epsilon del E by del T. I can write it this way. So what I'm getting is something like this. Now since it is a scalar quantity, we are having dot products, we can write it this way: mu h del h by del T minus, if I open up the bracket, I can substitute J as sigma times E. So if I write J as sigma times E, then the dot product of E and J will be what? It will be sigma times mod of E square. So this will become sigma times mod of E square minus epsilon E del E by del T. So now let us look at the first and the third term. We are having the product of a vector with its time derivative. So if I have the time derivative of, let us say, some vector v with its own dot product, then I can say this is nothing but the time derivative of the magnitude square. So which is also essentially nothing but 2v times del v by del t. This is a well-known vector differential identity where v is some time varying vector. So we can use this and apply this identity over here. So we can say now this divergence of E cross H becomes, this 2 will become a half once I represent it using this manner, minus mu by 2 time derivative of mod H the whole square, minus this will stay as it is, minus epsilon by 2 the time derivative of mod of E the whole square. Now, what we are seeing is, by calculating the divergence of the E cross H vector, we are getting some quantity in the differential form. But let us not forget what we are physically doing. We are trying to calculate what is the energy or the power that is being carried by the wave. So if that is the case, if we are trying to calculate the energy or the power carried by the wave, let us not forget that the wave is a continuous wave. It is existing at every point along the z-axis or at certain points in space, but the propagation of the wave is continuous. So since it is a continuous function, the wave, function of z or whatever, we should ideally write this power or the energy also in the continuous format, and that is not the differential format but the integral format. So the effective power or the energy will be obtained when we do the volume integral of this entire thing, because we are now looking at 3D space. So what happens now? If we use the volume integral, let us say this over the unit differential volume dV, that is nothing but minus so we should put the V sign over here showing it's a volume integral minus so now what we can do is on the left hand side we can actually use the divergence theorem and express this as an area integral. So the left hand side I can actually express this as E cross H dot dA, this using the divergence theorem, and the right hand side let me keep it same as the volume integral, but let me now group the like terms together. We can see that the H and E terms, that is the mu and epsilon terms, they look very similar. So therefore let us group them together. So since these are volume integrals and they are different from time, we can take the time differential outside and say minus del t, the volume integral of mu by 2 h square dV plus the volume integral of epsilon by 2 mod of E square dV minus this quantity. So now we had seen few minutes back that the unit of E cross H indicates power density or watt per meter square. So the watt per meter square, if we are integrating it over some area, what do we get? We get watt. So therefore this whole left hand side, which is the integration of the power density over the area of interest, this indicates power. So this is power. And in some sense, the right hand side will also indicate power, because if the left hand side is power, the right hand side also should be power. Now, this quantity E cross H is power density. That is nothing but power per unit area. This vector has a very special name. It is called Poynting's vector. P-O-Y-N-T-I-N-G, Poynting's vector. So Poynting's vector indicates power density, which is also a vector, as the name suggests. So the net power of the wave, as we derived it, is nothing but this. So we can see that there is clearly two terms which are carrying two power components. The first term indicates the power due to the E field and the H field components. So if there is a wave that is traveling in any medium which has some mu, some epsilon, this quantity, or rather these two integrals, will always be there, and it will be non-zero. So if you look at the dimension, it is nothing but a time integral, or sorry, a time differential of what? Of the energy. If you look at the quantities mu and h, this product essentially over the volume indicates energy, and this product also indicates the electric energy. This is the magnetic energy, this is the electric energy. So these two can never be zero so long as the left hand side is zero. So this cannot be zero for a traveling wave. Now what about the third quantity? Sigma E square. This indicates the loss in the medium because of the sigma term. So if the medium has some conductive nature or it's a very good conductor, then this term will start becoming significant. So this is nothing but the ohmic loss or dissipation in the medium. So the left hand side is E cross H, which indicates the total energy carried by the wave, or the total power. So that must be equal to the individual components which are either carrying the power or dissipating the power, as per the law of conservation of energy or power. So this is called Poynting's vector, and this theorem which says that the net power of the wave is divided among the electric and the magnetic energy components, and the loss is called as Poynting's theorem. Now let us look at some special cases of this Poynting's vector. So let us say I have an electromagnetic wave. We have a traveling electromagnetic wave which are functions of space and time. Without the loss of generality, let us say that it is in a homogeneous medium. So the wave has an electric component, let us say E, and a magnetic field component H. So since it is space and time varying, we can write the space component using some phi. So let us say this is E0 e raised to j phi e, where the phi e corresponds to the beta term and the space term. So phi e is essentially beta times z. So something of that kind, or minus, or whatever it is, we really don't care. And the time harmonic, which is e raised to j omega t, And let us say the E field vector is existing along some direction which is denoted by the unit vector E cap. So likewise we can define the magnetic field as some H0 e raised to j phi h, where again phi is something like this beta z, and the time harmonic j omega t, and the magnetic field is existing along an axis which is denoted by the unit vector h, where E and h must be perpendicular. So so now what we can do, let us try to calculate the instantaneous power, that is power at any point of time or time instant. So what we can do, we can essentially convert these into sinusoidals by taking the real values or real parts. So what would that be? We would get cos terms in both places. So the real parts we can find by writing E0 cos of omega t plus phi e times the E vector. And for the magnetic field, we will have H0 cos omega t plus phi h times the H vector. So the instantaneous power density, that will be nothing but the Poynting vector, which is E cross H. So since we are more interested in the active power, we have taken the real parts. So the power density is nothing but E cross H. So what do we get when we do the cross product of these two? So since these two are vectors, I can immediately isolate the scalar part from the vector part by saying that there will definitely be a vector product of E cross H, whatever that may be, and these two terms will be multiplied directly. So this is cos of omega t plus phi e times cos omega t plus phi h times this thing. So now we have a product of a cos and a cos. We can represent them using a sum of cos, which is nothing but E0 H0. I will have a 2 outside as half. So 1 will be the sum, that is cos 2 omega t plus phi e plus phi h. The other will be a difference. So omega t and omega t will cancel, leaving us phi e minus phi h times E cross H. So this is the instantaneous power density. So whatever be the values of the E field, H field, the phases, you will have to substitute them here and get it. Now, since this is a wave and it is a time harmonic wave, which means that it is definitely some function of a sinusoid, we can also define something called as the average power. Or the average power density, since it is a periodic wave. So how do I get this? So the average power density, so let us call this Poynting vector as some vector P. So I can define the average power density or the average Poynting vector P average, that is nothing but, as per definition, it is an integral over one time period of the Poynting vector. So P we already know what it is. It is this big thing, that's the instantaneous power density, which we are now integrating over one period of time. So what we are seeing is, whatever be the period, we will get something of this kind. So immediately we can see that this is a cos 2 omega t term, and therefore in one time period of the wave, this term will complete two cycles, two full cycles. So therefore the area under this curve will be 0. So effectively this disappears. What will remain is this quantity. So since this one totally disappears, I can say that the average power reduces to something of this kind. This is a constant, so this will stay. It is E0 H0 by 2 it is E0 H0 by 2 times the remaining term. So this disappears. What we only have is this cos of phi E minus phi H times the vector product E cross H. This is the average power density. So what we are seeing is that the average power density in general is independent of time. It is dependent only on the field magnitudes and the individual phases. But here we seem to be flying high without considering the effects of time. But somehow let us try to reintroduce the time harmonic in some way. So even let us try to express this average power using the time function. So what we can do is that rather than taking the real part, of the fields right away and expressing them using cos terms, we can introduce the time harmonic exponential and then take the real part of it later on. So I can say alternate definition of the average Poynting vector. So what we can write is this, if we assume is real and even this is real, what we are essentially looking for is the real part of the two time harmonics. So what we are doing is essentially this. So since we are taking a cos of a difference, I can also write the same thing over here. E raised to phi E minus phi H times E cross H. So if I expand this now, although I mean I don't mean that there is a time variable over here, because we are just trying to rewrite this using the time harmonic, but even though there is no time variable over here, what we see is that if we take this E0 and H0 terms inside, what we now get is this half times the real part of E0 times and let us also bring the vector product, the vectors over here, times the H0 e raised to minus JH. Now for the sake of convenience or the sake of clarity, let us introduce the time harmonic back. Now even though it is not a function of time as we have proved, we can always introduce the e raised to j omega t term and its reciprocal. So I can say this is nothing but times e raised to j omega t e, and I can introduce an e raised to minus j omega t term over here, thereby keeping the product as 1. So this is H0 e raised to minus j phi h e raised to minus j omega t h. Now does these two quantities look familiar? Do these quantities look familiar? Yes, they are nothing but the E and H vectors. But here the H vector is the conjugate. This is the E vector and this is the conjugate of the H vector. So I can say that I can redefine the average Poynting vector as nothing but half of the real part of the E vector cross the H vector conjugate. So now that we have defined this is a very interesting definition. And for continuous and periodic waves, often defining the average power is a very useful way to look at things. But now the question is there a condition when the average power density goes to 0? Now this can happen in two scenarios. One is hypothetically when the E field and H field vectors become parallel to each other. Now, although we know that in an unbounded medium that never happens, but supposing if by any means we make that happen. So if the E and H fields become parallel to each other, then the average power density becomes 0. So effectively it indicates that there is no power flowing. The other scenario when the average power can become 0 is when the intrinsic phase difference between the two fields becomes equal to 90 degrees. That is phi E and phi H. So let us write this down. So rewriting this thing, this is form 1. The second form or form 2 is when we can write it as E0 H0 by 2 cos of phi E minus phi H and E cross H. So P average can be 0 if the E and H vectors are parallel to each other. In that case, the cross product will nullify. Or the intrinsic phase difference, that is phi E minus phi H, between the E and H fields becomes 90 degrees or pi by 2. So these two things should never happen. So if you now go back and try to draw the fields, let us say that the E field exists along x-axis, the Y field exists along the H field exists along the y-axis, but both are functions of z. Then what will they look like? So let us try to draw them. So for the E field, let us say I can draw it something of this kind. The H field can be like this. So this is E and this is H. What you can see in this case, phi E minus phi H, that is the phase difference between the two field components, is 0. So this is definitely possible. So the wave is propagating in this direction. That you can easily prove by using the right hand thumb rule. The other possible scenario, let us say, for a traveling wave, this is Y, this is X, this is Z. Let us say the E field vector exists as before, but the H field vector has some phase. So everywhere there will be a phase. So here what you can see, there is a phase difference. So phi E minus phi H is non-zero. So if it so happens that the 0 of the H field coincides with the maxima of the E field, that is if they have a 90-degree phase difference, then effectively there will be no wave. There is no wave propagation as such. So therefore such conditions prohibit wave propagation and therefore any energy flow. So today we have completed most of the discussion on uniform plane waves, including how the waves exist inside different media, their velocities, whether the medium is dispersive or not, and after that we saw what is the average or what is the power or the energy carried by the wave. We represented that using something called as Poynting's vector and Poynting's theorem, which is also a consequence of the law of conservation of energy. And we saw that what are the conditions in which the fields should coexist to have non-zero energy flow. So therefore they should never be out of phase by 90 degrees. Any other phase is possible. And the second condition is that the fields should never be parallel to each other. So as long as these two conditions are ensured, we are quite happy having this. So we can ensure that wave is propagating with some finite power